On parity check, 0-1 matrix over ZP. Of content. We're going to start with the abstract, explain about what we're going to do. Then we'll go ahead into the introduction, explain a little bit further. In section 2, we prove some basic probability results that will be used throughout the paper. In section 3, here we have the upper bound and lower bound. In section 4 and 5, we give the M independence column over ZP, where each row is a tensor product of 0-1 matrices. So we expand our results. Then we have summary and our references. Before we go ahead and get into the abstract, we're gonna go over some definitions. A 0-1 matrix, a matrix whose entries are only 0 or 1, so it's a binary matrix. ZP, the set of integers modulo P, where P is a prime number. So a parity check 0-1 matrix over ZP, it's a binary matrix H with entries 0 or 1 defined over the finite field ZP. It defines a linear code C such that C has all the vectors or all the code words X such that HX transpose is equal to 0. So X is in the kernel space of H. Abstract. We prove that for every prime P, there exists a 0-1 matrix M of size T, n, where T is defined here, such that every M columns of M are linearly independent over ZP, the field of integers modulo P, and therefore over any field of characteristic P, and over the real numbers field R. In coding theory, this matrix is a parity check 0-1 matrix over ZP of a linear code of minimal distance m plus 1. Using the Hamming bound for p less than m and information theoretic argument for p greater or equal than m, it can be shown that the above bound is tight. We'll explain about this later in the paper. To reduce the number of random bits, we use n random variables that are m-wise independent. M-wise independent means any subset of up to m variables is jointly independent. This gives O m squared log squared n divided by log m random bits. We then use a new technique to extend this result to a 0-1 matrix of size Sn, where S is OT and m, and each row in the matrix is a tensor product of a constant d 0-1 vectors of size n to the power of 1 divided by d. This, for m, which is equal to n to c, where c is less than 1, is any constant, gives OM to 1 plus epsilon random bits for any constant epsilon. We'll explain about this later in the paper. We're going to use the matrix that we're going to prove that have such t rows to solve some well-known problems. The first problem is going to be the coin winning problem. Suppose that n coins are fake and each one has some different weight. We prove that there's a non-adaptive algorithm that finds the fake coins and their weights in this t weighings. There was a previous algorithm that could also solve this problem with the same complexity, but only for weights between n to the power of minus a and n to the power of b for constants a and b, and finds the counterfeit coins but not their weights. So we're gonna find also their weights, and we don't make them between any two numbers. We give them freedom. Another problem is going to be reconstructing graph from additive queries. Suppose that G is an unknown weighted graph with n vertices and m edges. There exists a non-adaptive algorithm. We're gonna show this algorithm that finds the edges of G and their weights in also OT additive queries. Previous algorithms solve the problem only for weights between n to the power of minus a and n to the power of b for constants a and b, and find the edges but not their weight. So this is very similar to the previous problem. Another problem that we have is the signature coding problem. Consider n stations, and at most m of them want to send messages from ZP through another channel. That is, the channel that's output is the sum of the messages. Then all messages can be sent, encoded and decoded with OT and M transitions. Previous algorithm run with the same number of transmissions only for messages in 0, 1. Simple information theoretic arguments show that all the above bounds are tight. We're going to show that the bounds are tight. We're going to show the algorithm later in the paper. So, introduction. A Tn01 matrix is called an M-independent column 01 matrix over Zp if every M columns in the matrix are linearly independent over Zp. In coding theory, this matrix is a parity check 01 matrix over Zp of a linear code of minimal distance m plus 1. A parity check matrix H, we said it's a matrix that defines a code O vector x such that Hx is equal to 0 mod P. Why, if any M columns are independent, the no-code word has fewer than m plus 1 non-zero entries? Because if X had at most m non-zero entries, then the corresponding M columns of H would satisfy Hx is equal to 0. Those M columns are linearly independent. Contradiction, because we assumed all sets of M columns are independent. So we proved that this code is a distance of m plus 1. Using the Hamming bound, we're going to explain about the Hamming bound when we get to this step, and information theoretic argument, it can be shown that such a matrix must have at least t rows, and t is defined here. This is also shown in the paper. We're going to show the lower bound and the upper bound. This gives a theoretical lower bound on how many rows t a matrix must have to achieve M independence. Using a straightforward probabilistic argument, it is easy to show that an OM log n cross n M-independent column matrix exists. Simply take a random 0, 1 matrix over Zp with such size and show that the probability that every M columns are independent over Zp is greater than 0. So if the probability is greater than 0, then such a matrix definitely exists. In subsection 3.3, we use BCH code to give a simple explicit construction of a M log n cross n M-independent column 0, 1 matrix over Zp. In this paper, this is the goal of the paper, we close the gap between the lower and upper bound. We prove that there exists a T cross n M-independent column 0, 1 matrix with T rows, and T is defined here. Give new analysis that shows that for any prime P and a random 0, 1 matrix of size T cross n, the probability that every M columns in M are independent over Zp is greater than 0. Our proof is based on the following results from number theory. Given a prime P and any sequence of M elements, we're going to call them S. We have A1 until AM. They belong to Zp over M. The number of subsequences T for which the sum of elements is equal to 0 is at most 2 to the power of M divided by minimum of these two. We're also going to prove this later in the paper. This is one of the lemmas. We're going to prove it. One application is the NM coin winning problems that we talked about earlier. Suppose that n coins are given among which there are at most m fake coins. The goal is to find an algorithm that finds the fake coins and their weights. We show that the above result implies that there exists a non-adaptive algorithm that finds the fake coins and their weights in t weighings, and t is defined here. Previous work, it solved the fake coin problems for weights between 2 to the power of minus a and 2 to the power of b for constants a and b. It also found the positions of the counterfeit coins, but not their weights. We can also find their weights in our algorithm. To reduce the number of random bits, we later then in section 4, we use n random variables that are m-wise independent. That means every subsequent up to m are linearly independent. This gives OM squared log squared n divided by log m random bits. We then use a new technique to extend this result to 0, 1 matrix of size S cross n, where S is O, T, and M by Nm. And each row in the matrix is a tensor product of a constant d01 vectors of size n to the power of 1 divided by d. This, for m equals to n powered by the power of c, where c is less than 1, is any constant, gives om to the power of 1 plus epsilon random bits for any constant epsilon. We're going to explain about this later in the paper. That we saw earlier is the problem of reconstructing weighted graph using additive queries. Let G be a weighted hidden graph where E are the edges and W is a function for the weights, and N is the number of vertices in V. Denote by M the size of E. Suppose that the set of vertices V is known and the set of edges E is unknown. Giving a set of vertices S, which is a subset of V, an additive query QS returns the sum of weights in the subgraph induced by S. That is, we go over all the edges that are in E and also in S, and we go over all the weights. Our goal is to exactly reconstruct the set of edges and find their weights using additive queries. See the many applications of this problem. Our result implies that there exists a non-adaptive algorithm to find the edges of G and their weights using O, T, and M additive queries. Previous algorithms solve the problems only for weights between n to the power of minus a and n to the power of b for constants a and b, and find the edges but not their weights. Another problem that we saw is the signature coding problem. Consider n station, where m of the stations want to transmit messages in ZP through another channel. That is a channel that its output is the sum of the messages. Then all messages can be transmitted, encoded and decoded in OT and M transmissions. Previous algorithms run with the same transmissions complexity in two stages. First, it decides which of the stations are active, that is, stations that want to transmit messages in 0 and 1, and then sequentially ask each active station to send its message. Our algorithm is non-adaptive and can detect the active stations and messages in one stage, and the messages don't have to be binary, not only 0 and 1. Simple information and theoretic arguments show that all the above bounds are tight. This paper is organized as follows. In section 2, we prove some basic probability results that will be used throughout the paper. In section 3, we give upper and lower bounds for M independent column, 0, 1 matrix over ZP. Section 4 and section 5, we give the M independent column 0, 1 matrix over ZP, where each row is a tensor product of 0, 1 vectors. Section 2, basic probability. In this section, we give some results in probability theory that will be used later in the paper. We denote by R the set of real numbers and by Z the set of integers. For a prime number P, we denote by ZP the field of integers modulo P. For any positive integer R, we denote by R the set 1 to R. And we will write for A plus B modulo P, we can write it this way. Let X be a vector or a matrix. We denote by weight X the Hamming weight of X, that is, the number of non-zero entries in X. For two vectors x and y, the distance dist xy between x and y is the number of entries in x and y that differ. That is weight x minus y. For sigma in 0, 1, we denote by sigma to the power of n the n vector, whose entry are all equal to sigma. We also denote by sigma to the power n cross m, the n cross m matrix, whose entries are all equal to sigma. And represent three lemmas and their proofs. The following three lemmas are well known from the literature over the field of real numbers. We give the proofs for any field ZP. The first lemma, lemma 1. Let A be in ZP but not the zero vector. Then, for a uniformly randomly chosen vector x we have the probability A transpose X equals to 0 modulo P is less or equals to half. Proof. Suppose that A1 is not 0, because we said A is not all 0 vector. So it has one entry at least that it's not 0, suppose it's A1. For any fixed x2 to xn, we have A transpose X equals to A1 x1 plus C for some C. Now, this takes the value C for x1 equals to 0. If we put here 0, then we have C, and if x1 is 1, we have A1 plus C. Since A1 is not 0, one of the values C or C plus A1 is not equal to 0. If both were 0, then we will have A1 equals to 0, which is a contradiction because we assume that A1 is not 0. Conclusion: the probability A transpose X equals to 0 is at most half, because there are only two possible values for A transpose X equals 0, C or C plus A1, and one of them is guaranteed to be non-zero. We said A1 is not 0. We can assume that because by making the assumption that A1 is not 0, we are simplifying the argument without limiting the generality of the proof. The reasoning will still apply, since all vectors A with at least one non-zero component can be transformed by permuting components into a form where the first component is non-zero. Or we can just say AI is not 0 for the ith entry that is not 0, which is guaranteed to have at least one like this. Lemma 2. Let M, a matrix, be anything but not the all zero matrix. Then for uniformly randomly chosen vectors x and y, we have probability that x transpose my is equal to 0 modulo p less than 3/4. Proof. By lemma 1, my has a non-zero entry with probability greater or equal to 0, to half, because we said the probability that it's 0 is less than half or equal. So the probability that it's not 0 is larger or greater than half. We assume that my is not 0. By lemma 1, the probability that x transpose my is not 0 is greater or equal to 0, which is the same concept. This implies the result, because x transpose my is not 0 in probability greater than half multiplied by half, which is 1/4. Then the probability that is 0 is less than 3/4. We're going to use this principle later in the paper, so we're going to explain about it. If you have more items than containers, then at least one container must contain more than one item. Lemma 3. Let A be the non-zero vector which belongs to that P, where P is a prime number. Then, for uniformly random chosen vector x, we have probability that A transpose x equals to 0 modulo P is less than the maximum of these two right here, where beta is defined here, alpha is also defined here, and we can see by simple math that beta is equal to 1 minus alpha divided by 2. Proof. Let S be this set, which is the distinct values that appear in the non-zero coordinates of A. We take two cases. The size of S is at most the weight of A to the power of alpha. Using the pigeonhole principle, there is an element G that appears in alpha more than the weight of alpha to the power of the weight of A to the power of 1 minus alpha times. We take the weight of A, we divide it by, because we know we have at most weight of A to the power of alpha, we can divide by it, and we have this result. Suppose that A1 to AT, there are equal to G, this element that appears more than weight of A to the power of 1 minus alpha times. Let T be the minimum of these two numbers right here. For any fixed xt plus 1 until xn, we have A transpose x equals to G multiplied by x1 plus x2 plus until xt, because we multiply a1 by x1, a2 by x2, and each of the a's until at are g, plus c for some constant c. Therefore, A transpose x equals to 0 implies that this sum should be equal to minus c multiplied by g to the power of minus 1. We just divided by it here. Since t is less than p, because we defined it like that, we have for c the probability that A transpose x equals to 0 is less than the numbers we see right here. We're gonna prove a one by one in the next slide. First step, probability that A transpose x equals to 0 is less than or equal to this number defined here. We want the probability that the sum of t independent random bits is equal to some fixed number modulo p, c multiplied by g to minus 1, we saw in the previous slide. We claim that the sum follows a binomial distribution because we're looking at a sum of independent Bernoulli half variables. S1 is the sum from x1 to xt, where hx belongs to 0 or 1 is chosen uniformly at random. This means each xi is 1 with probability half and 0 with probability half. Since the xi are independent, the sum follows a binomial distribution. We claim this is true because we saw in lemma 1 probability that A transpose x equals to 0 is less than or equals to half. So if we want probability A transpose x equals to 0, the worst case we can get is it being equal to half. The distribution of S1 is most concentrated around its mean. Its mean is half t. The probability that S1 equal to the mean is the highest among all possible values of S1. So the probability is never more than the peak, and the peak is given here, which we saw earlier. Because for a random variable S, which its distribution is binomial, the probability that S1 is equal to some k is given here, and we chose k to be the mean exactly. Next step, we use Stirling approximation and we get these results for t and t divided by 2. We open the definition of choose, we get this here. Then we approximate it by Stirling's approximation, and this is the result we get. We remember it's divided by 2 to the power of t. So we divide it by 2 to the power of t, and we get this. Remember, c was this number here, 2 divided by pi, and we have to the power of half. We get this result. Next, we have this. We remember the definition of t, and we remember that c is less than 1. We take the first one, we write it in a different way, and then we write the definition of t. We get this result right here. Remember that 1 minus alpha divided by 2 is beta. So we replace it, and we get the result. Okay, now to the case 2. The size of S is at least the weight of A to the power of alpha. For a set of elements Q, we have Q1 to QR, we denote by phi Q. These are all the sum where Y1 to YR could be 0 or 1. AQ are all the sums, but Z can be minus 1, 0, or 1. So it's a more expanded sum for all the combination. We said that S is more than weight of A to the power of alpha. So we argue that there exists a set of entries, Q, such that K is greater than this here, and phi Q is equal to 2 to the power of K. So, what are we trying to do? The idea is, if we can find a set Q such that phi Q is equal to 2 to the power of K, then the sum of A transpose X modulo P can take many values so the chance it lands on 0 is small. We prove this claim by showing how to find such set of entries. The process of finding the entries is iterative. At every iteration j, we have a set of entries q of size j such that phi qj is equal to 2 to j. It is easy to see that if a new member doesn't belong to AQJ, then if we added to QJ and we do phi, we get a new size of 2 to the power of j plus 1. We check with AQJ because it represents the set of all possible sums with coefficients from 0, 1, 0, 1, or minus 1 that can be found from the elements in QJ. And we need to check if adding a new member would lead to an increase in the number of distinct sums. It should introduce a new independent contribution to the linear combinations, thus increasing the size of the set. The number of distinct modulo P sums doubles. Each of the existing 2 to j sums can now either include the new member or not include it, resulting in 2 distinct outcomes for each. A new element can be added to Qj as long as this equation right here happens. We can guarantee that there's at least one element as long as this happens right here. Why? Because AQJ is defined as all linear combinations modulo P with coefficients in minus 1, 0, and 1. So there are at most 3 to j such combinations. If the size of S is greater than this, then some elements in S must lie outside of AQJ. This using the pigeonhole principle that we saw earlier. Therefore, we are able to find the set Q such that K is the size of Q and it's greater than log S, because we repeat this until 3 to K is greater than the size of S. Now, let W denote the set N, excluding the indexes I1 until Ik. For any fixed values for entries in W, we have that A transpose X is equal to, we take AI1, XI1 until AIK, XIK, and we do plus C, a new constant that represents the sum of all the indexes that are not included from I1 to Ik. By the properties of Q, there is at most one Y such that AI1 Y1 until AIK YK is equal to minus C. Why is this true? Because it was added in a way that forces different sums. Therefore, A transpose X equals to 0 is less than this here. We're gonna prove this later in the slide. First step, prove that A transpose X is equal to 0 is less than 1 divided by 2 to K, because there are 2k possible binary vectors. So there's at most one combination that makes the sum equal to any specific value. They are unique sums. So being equal to 0 is only one of them. That's where we get this from. Next, k is greater than log 3 weight A to the power of alpha. So we can write this right here. To the next step, we use this right here, so we can change it and we get our result because we know that weight of A, alpha log 3, 2 is greater than the weight of A to the power of beta, because we know alpha and we know beta. Note that lemma 3 is not true for non-prime P. We consider an even number P, then with probability half, we have P divided by 2. We can do this because P is even, multiplied by the vector x, x1 to xn, is equal to 0. If the sum is even, we can write it as 2r, then P divided by 2 multiplied by 2r is just P multiplied by r, which is 0 modulo P. We now prove some properties of the rank of random 0-1 matrices over ZP. Similar properties was proved for the field of real numbers in previous work. Lemma 4. Let M be a matrix of size Km of rank R, where R is less than M. For a uniformly randomly chosen row vector y, the rank of the matrix M tag, which is the matrix M and the row y, over Zp is R with probability at most half. The idea here is M tag consists of R independent rows, Mi1 until Mir, and one additional row y. If rank of M tag is equal to R, it means y is a linear combination of other R rows, else it would have increased the rank. Proof. Denote by Mi the ith column of M. Let Mi to Mir be any R linearly independent columns of M. Let Mj be any other column of the matrix, that is, J is not any index from the previous index we chose. There are unique constants A1 to AR such that Mj is equal to this right here, because it's definitely a combination, a linear combination of them. Else the rank of M wouldn't be R, it would be more than R, at least R plus 1. Therefore, we have this sum minus Mj is equal to 0. Let A be the M vector. Well, alpha j is equal to minus 1 because it's going to represent Mj, and all the alphas as we addressed here. And all the entries will be 0. So A transpose M is 0 because it's this exactly here, this equation. Then the probability that the rank of M tag is equal to R is less than probability that A transpose Y is equal to 0. Now by lemma 1 the result follows. The inequality holds because every Y such that the rank of M tag is equal to R, meaning we didn't increase the rank, must satisfy A transpose Y equal to 0 because it's a linear combination as we mentioned. But not every Y with A transpose Y equal to 0 necessarily lies in the row space of M. Lemma 5, which is going to be the last lemma for this section. Chernoff bound. Let x1 to xt be independent Poisson trials, such that xi is in 0 or 1, and the mean is equal to pi. Let p be the sum of all the pi's, and x be the sum of all the xi's. Then the probability that x is less than 1 minus lambda multiplied by p is less than e to the power of minus lambda to the power of 2p divided by 2. The idea here, if we perform many independent trials with an unexpected number of successes p, then for any lambda between 0 and 1, the probability that the actual number of successes is less than 1 minus lambda multiplied by p is very small. It decreases exponentially in lambda to the power of 2p. Section 3. M independent column 0-1 matrix. In this section, we prove the existence of an M independent column 0-1 matrix over Zp with optimal size. For completeness, we first give the lower bound. Section 3.1. The lower bound. The following lower bound follows from the Hamming bound, and using an information theoretic argument, we give the proof for completeness. Theorem 6. Let P be any prime number. A 0-1 matrix M, size of Kn, such that every M columns in M are linearly independent over Zp must have at least K rows, and we have the definition of K right here. Before we get into the proof, we're going to explain about the Hamming bound. Let C be a code of length n, with alphabet size q, and minimum distance d. The Hamming bound says, if we take the size of C, multiplied by the sum over all I chose n, and we multiply it by q minus 1 to the power of I, this is less than q to the power of n. If we have a parity check matrix M over Zp, this is how we're going to use this in our proof, where C is equal to the kernel of M, and K is greater than the rank of M. Then, the size of C is equal to p to the power n minus the kernel of m, which is less than p to the power of n minus k. Therefore, if we replace the size of c up here in the equation, we get this equation right here, which we're going to use later. Proof. For p less than m, and by the Hamming bound, we have the result we got from the previous slide. We can use Stirling approximation for log, which is written right here. Therefore, we can take this equation, put log on both sides, and we get this inequality. The second step right here is true because we take the largest element and only the largest element. On the left side, we add another element. On the right side, we only took one. So this step is true. This is equals exactly to this right here because log a multiplied by b is log a plus log b. So we use it right here, and that's exactly how we get our result. Because we saw that the Stirling approximation is exactly what we changed here. For p greater than m, notice that for every v, u, two vectors that are in 0 to m to n, of weight equal to half m, we have mv is not equal to mu. Otherwise, if they are equal, we get this inequality right, we get this equation right here, and the columns that correspond to the at most m entries that are not 0 in v minus u are linearly dependent, and this contradicts our assumption. Since for every v that is in 0 to m to n, of weight at most half m, we have mv that belongs to 0 until m to the power of 2 divided by 2. This is true because each entry of mv is the sum of at most m divided by 2 entries, because we saw that v has weight less than m divided by 2, and v lies in 0 to m. So the maximum sum per coordinate of mv is going to be m to the power of 2 divided by 2. We must have this right here. Why is this true? Because each mv is a vector of length k. Each coordinate is bounded by m to the power of 2 divided by 2, which we saw in the previous slide. So total number of distinct mv's is at most m to the power of 2 divided by 2. We take the less integer, add 1 to the power of k because we have k coordinates. This is where we got this equation from. mv is equal to this equation right here because we know that it has a weight of m divided by 2. So we do m divided by 2, choose n. We choose what entries we want to fill. And we have m minus 1 way to fill them because we can't fill them with 0. They are non-zero entries. We proved this equation. Now we can take log to the both sides and we get this right here. We use log a multiplied by b is log a plus log b, which we used here. We use Stirling's approximation and we get our result. Gilbert-Verschamal bound. GV bound is a classical result from coding theory that provides a lower bound on the achievable rate of error-correcting codes, giving a target minimum distance. Specifically, it guarantees that for any prime p, there exists a linear code over Zp of length n, which has minimum distance d and dimension of at least d log n divided by d. Equivalently, this implies that there exists a parity check matrix M, size k, n, such that every set of d-1 columns is linearly independent. How we're going to use this? In our context, we seek a matrix M over Zp such that every set of m columns is linearly independent. This is exactly the dual condition required for a parity check matrix for a code with minimum distance at least m plus 1. Upper bound and generalization, section 3.2. It is easy to prove the following. See the first part of the proof of Theorem 8. Theorem 7. For any prime P, there exists a matrix M such that K is equals to O M log n divided by M, and every M columns are linearly independent over ZP. Notice that this bound meets GV bound, exactly what we showed in the previous slide. An explicit construction with the same bound is given in the next subsection. The following theorem closes the gap between the upper and the lower bound. We gave this at the lower bound, and we're going to show this at the upper bound, so we close the gap. Theorem 8. For any prime number, p, which is less than n to phi, for some constant phi, there exists a matrix M to the which have size kn, such that k equals to this number right here, we prove to be the lower bound, and every M columns are linearly independent over ZP. Proof. Let T be equal to M divided by log squared M. We first prove the existence of a matrix M star, which has size K1n, such that K1 is T plus log T plus 2 log T choose N, where every T columns are linearly independent. We use probabilistic method. We randomly uniformly choose K1 vectors of size n to be the rows of the matrix. Denote by Mi the ith column of matrix M star. Now, let Mi1 to Mit be any T columns. We're gonna prove that they are independent. And we consider the new matrix M tag, which has Mi1 to Mit. We can see that rank of M tag is at most T because it's of size Kt. Let M tag J be the jth row of M tag, and M tag J with this symbol be the first J rows of M tag. Consider the random variable xj, which belong to 0 and 1, where xj is equal to 1 if and only if the rank is equal to T, or the jth row mj increases the rank of mj minus 1. By lemma 4, we have probability that xj is equal to 0, giving x1 to xj is less than or equal to 0. And this is reminder for lemma 4. Therefore, the probability that the rank of the matrix M tag is smaller than T is bounded by the probability that the sum of these x, K1, is less than T minus 1. We write this in a different way, where each constant is equal to 0 or 1. It's the same concept. And we're gonna show why it's less than this here and all the other steps. Using union bound, the probability that there exists a set of T columns that are linearly independent is less than half. This implies the existence of M star. We took the second step, we're gonna prove it right here. The chance that xj is equal to 1 is at least half. Worst case is where probability that xj equal to 1 is half, because we try to make them dependent. So xj is Bernoulli with half. The worst case is when each xj is independent. Exactly. S is equal to the sum of x1 until xk1, and it's binomially distributed. Probability that S, which is binomially distributed, is less than T minus 1. This is a known result from binomial distribution. We get the result right here, which is exactly our result. Next step, we prove this right here. This is true because the denominator on the right is smaller than the one on the left, because we have the definition of T at K1. Next step is gonna be this one. We have T terms, and each term is less than T choose K1 here. So we can take t choose k1. We said we have t terms, and we wrote the denominator in a different way. And that's how we get our equality right here. Reminder for the union bound. For any events A1 to AR, the probability that we have the sum of AI is less than if we sum the probabilities of each event. So, the probability that at least one of the bad events occurs is no more than the sum of the probabilities of each one individually. That's how we continue our proof. To this step, we want to bound the probability that any set of t columns is linearly dependent. For a fixed set of t columns, the probability that they are dependent can be bounded by this number right here that we showed earlier. There are t choose n subsets. By union bound, we can bound this right here. We can choose k1 large enough so that the inequality holds. The denominator grows exponentially. This showed that with positive probability, no set of t columns is linearly dependent. Therefore, such a matrix exists. Now, we have a matrix M star that every m divided log squared m columns are linearly independent. We add k2 uniformly randomly chosen row to the matrix, where k2 is equal to m log p add log m choose n divided by log q, where q we defined it right here. Since every m divided by log squared m columns in M star are linearly independent, every t columns in M are linearly independent too. A pending row never destroys linear independence of its columns. Therefore, if mj1 to mjm are columns of M, and lambda 1 to lambda m satisfies the quality right here, we know that the MIM are dependent. Then at least m divided by log squared m of the lambda i's are not zero. We can assume for contradiction that fewer than them are non-zero. That means we have a linear dependence within less than t columns, which we said was not true. Therefore, by lemma 3, the probability that some m columns mj1 to mjm are linearly independent, we can write it as follows. Probability that we have m columns and m lambdas such that the sum is equal to 0. And this is less than this right here. We explain it here. Choose any subset of m columns from the n total columns. We can choose m choose n. For each subset, we choose a non-zero vector lambda, which each one has we have p to the power of m minus 1 vectors, because we can exclude the all zero vectors, and this is less than p to the power of m. That's how we get this step. Now for the next step, this equation must hold for all the k2 random rows we've added. So for lemma 3, the probability that the sum of lambda I mji is equal to 0 is less than q to the power of minus k2. The more random rows we add, the smaller q to the minus k2 becomes, exponentially decreasing. We can choose k2 large enough to make the product less than half, because we used lemma 3. Here's a reminder for lemma 3. Therefore, the probability that there exists m column of m that are linearly dependent is bounded by half. This, together with the fact that k1 plus k2 is equal to this right here, implies the result. k1 plus k2 is equal to this right here because k2, we have, this is the definition, and this is the definition of k1. Now, we have this approximation that we saw also earlier, and we know that q is the minimum of these two numbers. This is the definition of q. So log q is approximately equals to the minimum of these two right here. We did log 2 to the power of beta and log 2 p to the power of half. We get this result. Since log t is almost log m, we get that this result is true. We can use this corollary we're going to prove here to solve two of the problems we saw earlier, the coin weighting problems and the signature coding problem. There exists a matrix M where k is equal to this number defined here, and for every two distinct vectors x, y such that the weight of x is less than m and the weight of y is less than m, we have mx is not equal to my. So, giving m and x equal to some number, we can always know what x this number was because only one x could have gave us the result. Proof. Choose a prime 2m less than p. By theorem 8, there exists a Kn matrix M such that every 2m columns are linearly independent over Zp and therefore over R. For any two vectors x, y such that the weight of x is less than or equal to m and the weight of y is less than or equal to m and x is not equal to y, so they are different vectors, we have the weight of x minus y is between 0 and 2m, at most 2m different entries. Therefore, m, if we multiply it by x minus y, is not equal to 0. Therefore, mx is not equal to my. mx minus y is not equal to 0 because else not every 2m columns are linearly independent and we have a contradiction. We will now show how this solves the coin winning problem. We said the coin winning problem is that we have n coins, where at most m coins are fake. Each row of m will represent a subset of coins to weigh. Each entry is equal to 1 if coin j is included in weighing I. So, we have n columns and k measurements. For any two distinct sparse vector x1, x2, we showed mx1 is not equal to mx2. The observed sum y equal to mx uniquely determines which coins are counterfeit. Y represents total weights per weighing. We find x, each coordinate j corresponds to the coin j. If xj is not equal to 0, the coin is fake, and its weight is xj. We can assume that the real coins have weight of 0. So we found the weight xj, and we found which coins are fake. The signature coding problem is similar because we have n station, at most m are active, y will be the sum of their messages. Subsection 3.3. An explicit construction. Explicit m-independent column 0,1 matrix M over R was studied in an area of compressed sensing of sparse signals. We can also see the reference papers. In compressed sensing of sparse signals, the goal is also to be able to decode mx, which is find x from mx, in near linear time, when x is m sparse. That is, when at most m entries in x are not zero. Previous algorithm gave an explicit construction of size of m multiplied by 2 to the power of log n squared that have near linear decoding time. His construction can be applied to any field Zp. What is BCH code? BCH code is linear error correcting code with as well structured parity check matrix. The matrix had the property that any m columns are linearly independent, exactly what is needed for sparse recovery in this paper. In the subsection, we give an explicit m-independent column 0,1 matrix over Zp and R of size O m log n. Our construction is based on BCH code over Zp. Decoding time of BCH code over Zp can be done in O n poly log n time. For the field R and fields of characteristic 0, one can use the BCH code over Z2. This is because independent columns over Z2 implies independent columns over R, but it's not clear how to decode MX over R. Independent columns over Z2, we use coefficients only 0 or 1. So it has to be that they are also independent over R. To build such matrix, we first build a matrix over ZP with entries from ZP, and then write each entry in its binary representation as a column vector. To formalize this, consider an integer L, such that P to L is greater than N, which is greater to P to L minus 1. This ensures that the field GF has at least n distinct elements. GF is the finite field with P to L elements. Consider this field and a primitive element alpha. This means alpha generates all non-zero elements by its power, proven to exist. Consider the first n columns of the parity check matrix of the primitive BCH code over GF. We have this matrix V. Every alpha to I can be written as alpha I some scalar multiplied by alpha to some power. The set 1 to alpha to L minus 1 is a basis if and only if alpha is a root. And we said that alpha is a root, so we have this is a base, and we can write each alpha to I by the base. For Q, let bin Q be the binary representation of Q, where R is equal to log P and Q has entries 1, 2 to the power of 2 until 2 to the power of R minus 1 multiplied by binary Q, which is going to help us write Q in the binary representation. And we define beta I, a vector that is the binary representation of each Zi we saw. Zi0, Zi1 to Zil-1. This vector beta I is now a binary encoding of the field element alpha to I, because we said that alpha I can be written as Zi multiplied by alpha to some power. And it has length of R multiplied by L, which is log n, because there are L entries, each one has R, because we said that R is log P, so it has R columns. And we know that P to the power of L is greater than N, this is what we assumed, so L is greater than log N divided by log P. We now prove lemma 9. The 0, 1 matrix W, which has beta 0 to beta n minus 1 until beta n minus 1, is of size m log n, and every m columns in W are linearly independent over Zp. Proof. Suppose for the contrary that there are m columns in W, where I is in n, that are linearly dependent. Then for every j from 1 to m, we have the sum of lambda I multiplied by beta ji is equal to 0 for some lambda I that are not all equal to 0. Therefore, if we remember the definition of beta ji, it was binary of Zij s for all j from 1 to m and s from 0 to L minus 1. Therefore, if we go over all j's from 1 to m and s from 0 to L minus 1, we remember that this is equal to 0, and we multiply it by another number, so it's still equal to 0. That's why the first quality holds. Then we can move this 1, 2 to the power of 2 until to the power of R minus 1 to the next sum, because it's not dependent with S. We notice that this is exactly Zijs. That's how we define Zijs, or any number. It's the binary representation multiplied by the vector 1, 2 to the 2 to the power of R minus 1. So that's why this quality holds. Now we can move here, we can move the Zijs to the alpha to the power of s, because we still go over the sum of I. And we remember that this is exactly alpha to the power of ij, because that's exactly how we define them. So we got that there's an M independent column in V, which is a contradiction because we know the base is independent. Section 4. 0, 1 matrices with rows that are tensor product of two vectors. In this section, we show that there is an M-independent column, Tn 0, 1 matrix, that its rows are tensor product of two 0, 1 vectors in 0, 1 root of n, and T is defined here. In the next section, we extend this result to 0, 1 matrix that its rows are tensor product of d 0, 1 vectors in 0, 1 n to the power of 1 divided by d. Before we continue, we're gonna mention the tensor product. Let A and B be two vectors, then the tensor product is defined as follows. We multiply each entry in the vector, the first vector, by the second vector. So it's a big vector where each entry of A scales all of B, stacked together. The following theorem follows from case 1, the proof of theorem 11. So its proof will be in theorem 11, but we're going to mention it here because we're going to use it later. Theorem 10. Let P be a number less than n to the power of phi. Let P be a prime number for some constant phi that is greater than 1. There exists a set of S pairs x and y, where xi, yi is 0, 1 to n, and k is defined here, such that for any matrix A that is in Zp of size n by n, which is not the zero matrix, with the weight of A being less than m or equal to m, there exists an I such that xi transpose A yi is not equal to 0 modulo p. Now prove the following. Theorem 11 is very similar to Theorem 10. The only difference is how k is defined. We have same input. P is a prime number less than n to the phi for some constant phi that is greater than 1, and a set S that has k pairs where xi, yi is in 0, 1 to n, and k is defined here, such that for any matrix A that belongs to Zp size n, which is not the zero matrix, with weight of less than or equal to m, there exists an I such that xi transpose AYI is not equal to 0 modulo p. We first noticed that when m is constant, then O of m plus m log n squared divided by divided by log minimum of mp becomes exactly the theorem 10. Because m is constant, so we can ignore this term right here. Log minimum will become a constant 2, so we're left with m log n squared divided by m. Therefore, we may assume that m grows without bound. It eventually grows larger than any constant. Note that also we can assume that m is less than n squared divided by 2. Otherwise, we can just take all the n2 pairs because O will be n squared. This term will be gone, will be constant, and we're left with OM, and m is greater than n squared divided by 2, so we can choose n squared pairs, and because A is a non-zero matrix, at least one entry is not zero, and the base will catch it. Now we have a set of matrices that we want to divide. This set will be all the matrices A of size n by n, which belong to Zp, but not the zero matrix, which have a weight less than or equal to m. We divide them into three non-disjoint sets, meaning they can have overlapping elements. The first set will be all non-zero matrices A, such that the weight is less than m divided by log m. A2 will be the set of all non-zero matrices A such that the weight of A is in between m divided by log m and less than or equal to m. And there are at least the root of m divided by log m non-zero rows. A3 will be similar to A2. The only difference is instead of rows will be columns. We note that for any matrix A of weight more than D, where D is m divided by log m, either A has more than root of D non-zero rows or more than root D non-zero columns, meaning it belongs to the set A2 or A3. Suppose A has at most root of D non-zero rows and at most root D non-zero columns, then the maximum possible numbers of non-zero entries in A is bounded by the product of these two quantities. So the max non-zero number of entries will be D. But this contradicts the assumption that the weight is more than D, is greater than D. Therefore, A is exactly A1, A2, and A3 together. Using the probabilistic method, we give three sets, S1, S2, and S3, of vector pairs, such that for every j, 1, 2, or 3, and A that is in set Aj, there exists a pair of vectors xy that belong to Sj such that x transpose Ay is not equal to 0 modulo P, and the sizes of all these sets, S1, S2, and S3, are all gonna be together O m plus m log n squared divided by m, all divided by log minimum of mp, which we saw earlier. Case 1. A belongs to A1. We remember the weight of A is less than m divided by log m. By lemma 2, which we have a reminder for right here, for randomly chosen vectors xy and A that belongs to A1, we have the probability that x transpose Ay is equal to 0 is less than or equal to third quarters. We randomly uniformly choose k1 vectors. K1 is defined right here, and we can see that it's greater than c m log n squared divided by log m. This is true because log minimum of mp is less than or equal to m, and here we have it as a denominator, so we can have this inequality right here. And c is defined right here. Then the probability that for all xi, yi we have xi transpose a, yi is 0 is bounded by third quarters to k1, because we want all the pairs to have this quality right here. Therefore, by union bound, the probability that there exists a matrix A of weight smaller than m divided by log m such that xi transpose a, yi is equal to 0 for all I that are in k1 is less than this right here. We will go over each term one by one. M log m chose m divided by log m choose n squared is the number of ways to choose which entries are non-zero, because we know A has at most m divided by log m non-zero entries. P to the power of m divided by log m is the number of ways to choose the values of these non-zero entries, because each non-zero entry has p minus 1 option, and it's bounded by p. Third quarters to k1 is the probability that all k1 tests fail for a fixed matrix A, which we saw in the previous slide. We then have this step in the proof. This is true because we have a binomial upper bound. We can take log for both sides, and we can see that this inequality right here is true for large m, which we know m grows eventually larger than any constant. This explains how we got from this term to this term right here. We know that p is less than n to the power of p, so we can replace it. We get this right here. For the last term, third quarters to k1 is less than 2 to the power of minus 0.415 k1, which is k1 divided by 3. Then we have these steps right here that we're going to see why they are true. First, we have the same base, so we can add 2 plus phi. This is how we go from this to this. We know that k1 is greater than this number right here that we saw in the previous slides. That's why this inequality holds. M log n squared, we can take the 2 here because this is one of the log properties. And then we use this property right here to replace the 2 and the n. So we get this quality right here. The last step is we replace the c by its definition, and this is less than 1 because this is a negative number. This is overall a positive number with a minus sign, so it's n to the power of a number that is negative. So this is less than 1. Case 2. A belongs to A2. We start by proving the following two lemmas. Lemma number 12. Let U be the set of all non-zero vectors with weight smaller than m to the power of third quarters. For any constant c, which is greater than 1 plus phi multiplied by 16 divided by log e, and k2, which is defined right here, this inequality holds because we said log minimum mp is less than or equals to m. So when it's in the denominator, we can flip the inequality. And here, because m log n squared divided by m is equal to m log n squared minus m log m divided by log m, we have the minus m right here. There exists a multiset of 0, 1 vectors y from y1 to yk2 such that for every u that is in U, the size of the multiset yu, which is the indexes I, for which u transpose yi is not equal to 0, is at least k2 divided by 4. Proof. By lemma 1, for a randomly chosen vector y and any u that belongs to U, we have the probability that u transpose y is equal to 0 is less than or equal to half. Therefore, if we randomly uniformly choose the vectors of y, then the expected size of yu is greater than k2 divided by 2, because we have k2 pairs in y. Using Chernoff bound lemma 5, we have that the probability that the size of yu is less than k2 divided by 4, this equals the probability that the size of yu is less than 1 minus half multiplied by k2 divided by 2. Then we can use lemma 5, where lambda is half and p is k2 divided by 2. We get this inequality right here. Therefore, the probability that there exists u that belongs to U such that the size of yu is less than k2 divided by 4 is the size of u multiplied by the probability. The size of u, this probability is less than e to the power of c divided by 16 n log n squared divided by log m, because we saw that k2 is greater than this number. The size of u is m. We go over the sum from 0 to m to the power of 3 quarters, because we said that the weight is less than third quarters. We choose I entries. For each entry, we have p possibilities, or p minus 1 to be exact, because we can't choose a 0 entry. We now explain why this is true. The first step is true because here we go over the sum of 8 to the power of 3 quarters of many terms. We take the largest term, which is when we put I as m to the 3 quarters, we get this right here. We multiply it by how many times we add this sum. Then we know that p minus 1 is less than p, and p is less than n to the power of phi. That's why this step is correct. We can get rid of the m to the power of 3 quarters because it's small relevant to n to the power of m to the power of 3 quarters. We know c is greater than this number right here, so this explains why the denominator is less than 2m divided by log m, and we subtract the power. This is negative, this number is negative for large m, and we know that m is very large. So this implies the result. Note that the constant c will be determined later in the proof. Now, for the next lemma, lemma 13, we define for non-negative integer r, LR, which is the minimum of Rp if r is greater than 0, and if r is 0, LR is equal to 1. Lemma 13. Let m1 to mk2 be integers in m and 0, such that the sum of all these m's equals to L, which is greater than k2. Then, if we multiply LMI for each I between 0 and k2, this is greater or equal to the minimum of mp to the power of L minus k2 divided by m minus 1. We first prove that when m1 is greater than 1 and less than m2, m2 is less than m, then this inequality right here holds. We have 4 cases. First case, p is less than m1 minus 1. Then, this inequality right here gives us p squared is less than or equal to p squared, because this is going to give us p. This also is going to give us p since m1 is less than m2. And same here. Second case, when p is equal to m1, then 3 gives us p minus 1. This is going to choose m1 minus 1, which is p minus 1. This is going to choose p as the minimum. This is also going to choose p, and this is also going to choose p. Third case, when p is greater than m1 but less than or equals to m2. The first term gives us m1 minus 1. The second term definitely gives us p. And here we get m1, and here we also get p. Last case, when p is greater than or equals to m2 plus 1. Then we have this as m1 minus 1, and this as m2 minus plus 1, and m1, m2. And this is also correct. In all cases, the inequality is true. Here we can see that m1 multiplied by m2, we get it from the first term. m1 multiplied by 1, we have m1 minus m2 minus 1. m1 minus m2 is negative, since m1 is less than m2. So we have m1 multiplied by m2 minus a negative number, minus a number. So this is less than m1, m2. Also, we notice that when m1 is equals to 0 and m2 is greater than 1 but less than m, then we have m1 plus 1 is going to be L1, which is 1. LM2 minus 1 is going to be the minimum of m2 minus 1 and p, by definition, which is less than the minimum of m2 and p, which equals to LM1 because this is 1, LM2 because this is the definition. Therefore, the optimal value of LM1 to LMT is obtained when for every ij, we either have mi as 1 or m, or mj as 1 or m. In this way, we guarantee smaller product of multiplication and still reach sum greater than k2. This is the 2 constraints that we have. This is equivalent to all mi is 1 or m except at most 1. Why is this true? Because for each 2 values, we can make the first one reach the number 1 or the second value reach m. That's what we saw in the previous slide. This implies that at least L minus K2 divided by M minus 1 of the mi's are equal to M. We're gonna see why this is true in the next slide. T of the mi's are equal to M. The rest, K2 minus T, are equal to 1. This is what we are assuming. The total sum is, we go over the sum of mi. We have T multiplied by M, because we have Tn's, plus K2 minus T multiplied by 1. That equals T multiplied by M minus 1 plus K2. We are told that the sum of mi's is equal to L. So we get Tm minus 1 plus K2 is equal to L. We solve for T, we get this result. Now, let U be the set of vectors defined in lemma 12. Let A, B belong to A2. Since the weight of A is less than M or equal to M, there are at most M to the power of 1 divided by 4 rows in A with weight greater than M to the power of 3/4. If there were more than M to the power of 1 divided by 4, we can multiply it by M to the power of 3/4 and we'll get more than M entries, which is not correct. Therefore, there are at least Q. We define Q as M divided by log M root minus M to the power of 1 divided by 4, 4/4 rows in A that are in U. Let AU be Qn matrix that its rows are any Q rows in A that are in U. Let Y be a set Y1 to YK2. The set we proved its existence in lemma 12. Note that if we go over the sum of the weight of AU multiplied by YI, this is greater or equal than QK2 divided by 4. For every row, at least Q2 divided by 4 of the weight AU YI are non-zero. Since the weight of AU YI is less than or equal to Q, since AU YI is a vector of length Q, for all I, which belong to 1 to K2, by lemma 13 we have, if we go over the multiply of each L of the weight AU YI, this is greater or equal to the minimum of QP to the power of Q K2 divided by 4 minus K2 divided by KQ minus 1. We set the MIs as the weight of AU YI and L the sum of each MI, which we saw is greater or equal than Q K2 divided by 4. This is greater than or equals to minimum QP to the power of C1 K2, where C1 is a constant. And we can see that this is greater or equal to the minimum of MP, where to the power of C2 K2, where C2 is also a constant. We here have a reminder for lemma 3. The next slide, we're going to use this lemma. If we randomly choose x1 to xk2, then by lemma 3 we have the probability that for all I in k2, such that xi transpose ayi is not equal to 0, is less than the multiply of 1 divided by the minimum of the weight of ayi to the power of beta and p root of p. This is from lemma 3. This is less than or equal to 1 divided by L weight of ayi to the power of beta. We remember this is the definition of the minimum of the first entry, and p. P to the power of beta is greater than p to the power of half, but as a denominator, we get that this inequality is true. This is less than or equal to 1 divided by LW weight of AU YI to the power of beta, because AU is a subset of A. This equals as if we got the power of beta outside. This is less than or equal to 1 divided by minimum MP, which we saw in the previous slide and proved, multiplied by beta C2K2, which is equal to the minimum of MP to the power of minus C3K2, where C3 is a constant. Therefore, the probability that there exists a matrix A in A2 such that for all xi, yi, we have xi transpose ayi is 0 is the probability that there exists an A in A2 such that for all I in K2 xi transpose ayi is equal to 0 modulo p is less than or equal to the size of A2 divided by the probability we saw earlier. The weight of A for an A that belongs to A2 is less than or equal to M. So we can choose up to M entries. For each entry we have P possibilities. This is a well-known inequality, so we use it right here. And we know that K2 is greater than C multiplied by this number right here. For p less than m, since m is less than n squared divided by 2, the above is less than 1 for c3 multiplied by c that is greater than 3. We here substituted m for n squared divided by 2. From simple math, we get this is the result, which is less than 1. For p greater than or equal to m, we get that this term, the minimum of mp, is now m, so this cancels this term. We know that p is greater than m, so this is less than if we put m here, which cancels this terms right here. We subtract the power, and we get this is less than n to the power of minus m, which is less than 1 for c greater than this number right here. Case 3. A belongs to A3. Let S2 be the set of vectors we prove their existence in case 2. We define S3 as the reversed pairs. We argue that S3 is the desired set we are looking for. For any A in A3, we have that A transpose is in A2, because now the rows has less than the number we defined earlier. Therefore, there exists I such that xi transpose A transpose yi is not equal to 0. This is case 2. Note that since this is a scalar, the transpose is equal. So we get this yi transpose axy not equal to 0. This is the set that we define. So this implies the result. Now we can prove our main result. Corollary 2. There exists a matrix M, size k n, where k is defined right here, and every row of M is a tensor product of two vectors x, y that belong to 0, 1, n, the root of n. And every m columns of M are linearly independent over Zp. In particular, the same matrix is 0, 1 matrix with m independent columns over any field of characteristic P over the real field R. We have a reminder for theorem 11. Let P be less than n to the power of phi, a prime number for some constant phi greater than 1. There exists a set of k pairs, where we have the definition of k right here, such that for any matrix A, which is not the 0 matrix, with weight less than or equal to m, there exists an I such that xi transpose AYI is not equal to 0 modulo P. Proof. Assume n is a perfect square. Let S be the k vectors, the set we found in theorem 11, with vectors in 0, 1 to the power of root n. Define the matrix M, where the ith row is the tensor product of xy, xi, yi. We argue that every m columns of M are linearly independent. Suppose, on the contrary, that there is a set of columns mi1 to mim that are linearly dependent. Then there are constant alpha 1 to alpha m that are not all 0, such that this combination is equal to the vector 0. We define the following matrix A, which belongs to Zp, size root of n by root of n. For every column's index ij, let the entry uv of the matrix be equal to alpha j, where u is ij minus 1 divided by root of n plus 1, and v is ij minus 1 modulo root of n plus 1. All other entries are 0. We can see that xi transpose AYI equals to the ith entry of the vector alpha 1 mi1. We add all until alpha m mim. Therefore, we get that xi transpose AYI is equal to 0 because this is 0. So each entry in this vector is also 0 for all I. Since A is not the 0 matrix and the weight of A is less than m, we get contradiction. Corollary 3. There exists a set S with k pairs where xi, yi is in 0, 1 to n, and we have k defined here, m log n divided by log m, where for any matrix A, size n, such that the weight of A is less than or equal to m, and A is not the zero matrix, there exists an I such that xi transpose AYI is not equal to 0. We see here that now the matrix belongs to the R field, not the ZP field. Proof. Again, we argue that the set S found in theorem 11 is the desired set. Let A be a matrix. Let AI denote the ith row. Define the n squared vector, which is AV, which is going to be A1, A2 until AN. So we have the rows expanded. Then, for any xy vector, which is in 0, 1 to n, we have x transpose AY is equal to the tensor product of x and y transpose AV. X transpose AY, we go over all the sum of xi, aij, yj, and this is exactly the tensor product, because in the tensor product vector, the ij coordinate is xi, yj. Define the matrix M, where the ith row is xi, the tensor product of xi, yi. In the previous corollary, we showed that every m columns of M are linearly independent over R. Now, suppose that there exists a matrix A such that the weight of A is less than or equals to M, and for all I from 1 to k, we have xi transpose AYI equal to 0. Since x transpose AY is equal to the tensor product of xy transpose AV, and xi transpose AYI is equal to 0 for all I from 1 to k, we get that M, the matrix we defined, multiplied by AV, the vector we defined, is equal to a vector of all zeros. This is a contradiction, since the weight of AV is equal to the weight of A, which is less than M, and every m columns of M are linearly independent. We left one problem without a solution, so we're now going to provide an algorithm that solves it. Consider the following problem of reconstructing weighted graph using additive queries. Let G be a weighted hidden graph, where E, the edges, W is a weight function, and N is the number of vertices in V. Denote by M the size of E. Suppose that the set of vertices V is known, and the set of edges E is unknown. Giving a set of vertices S, which is in V, an additive query QS returns the sum of weights in the subgraph induces by S. That is, we go over all the weight function for the edges that are in S. Our goal is to exactly reconstruct the set of edges and find their weights using additive queries. We consider a variable xi for each node vi in V. Define for each subset of vertices v tag in V a 0, 1 vector AV tag, where AV tag index I is equal to 1 if and only if Vi is in V tag. We consider the matrix AG, where AG in entry ij is equal to the weight of Vi Vj, if and only if Vi Vj is in E, the edges, and AG in the entry ij is equal to 0 otherwise. It is easy to see that AV transpose AG AV tag is equal to 2 multiplied by Q V tag. We count each edge twice, once as ij and once as ji. So AG is a symmetric matrix, and therefore we have this quality right here. So the Q oracle is equivalent to the assignment oracle of the function x transpose AG x over the domain 0, 1 to n. The problem now is to reconstruct a symmetric matrix A using the assignment oracle to FAX, x transpose AX, over the domain x in 0, 1 to n. Grabinski and Kocherov show that for any symmetric matrix A, one can turn this oracle to an oracle to FAXY, which is X transpose AY, in 5 queries. The following shows that 4 queries are sufficient. Let X be a vector and Y also be a vector, and we define this is the joint X and Y, X or Y, and this is the opposite of X. Then, X transpose AY is equal to these 4 queries. Careful algebraic expansion of each quadratic term and adding or subtracting them as in formula yields exactly 2X transpose AY. We then divide it by 2, which gives us the quality X transpose AY. Each term on the right side is a quadratic form, so we can compute each term by 1 query. We now prove corollary 4. There exists a non-adaptive algorithm that uses K, which is O m log n divided by log m, additive queries, and reconstruct any weighted hidden graph with at most m edges. Proof. From corollary 3, it follows that there exists a set S with k pairs where xi, yi is in 0, 1 to n, and k is O m log n divided by log m, where for any matrix A in R, which have size n by n, such that the weight of A is less than 4m or equal to 4m, and A is not the zero matrix, there exists an I such that xi transpose AYI is not equal to 0. Now, we use xiyi to find zi, which is xi transpose AGYI. We claim that the answers zii uniquely determines AG. Otherwise, there are two weighted graphs G tag, which are not the same, with at most m edges, such that for all I, xi transpose AGYI is equal to xi transpose AG tag yi. This implies that for every I, xi transpose AG minus AG tag yi is equal to 0. Since the weight of the weight of AG minus AG tag is in between for m and 1, we get a contradiction because we said they are not dependent. 5. Section 5 is the last section here, which is about matrices with rows that are tensor product of vectors. In this section, we show that there is an m-independent column Tn01 matrix, that its rows are tensor product of D01 vectors in 01 n to the power of 1 divided by D, and T is defined here. Here we have some definitions. I'm not gonna go over them and read them, but we have them here stated and clear. Same goes for this slide. We first prove the following. Theorem 14. Let P be a prime number less than n to the power of phi for some constant phi. There exists a set S x1 1 to x1d, x2 1 to x2d, until xk1 to xkd, where xij is in 0, 1 to the power of n, and k is defined here, such that for any d-dimensional matrix with weight of A being less than or equal to m, there exists an I such that the entry A in this place is not equal to 0. This is going to be similar to what we did earlier. We divide the set of matrices A, where A is nzp to the power of dn, but not the zero matrix, weight of A is less than or equals to m, into D plus 1 non-disjoint sets, meaning they can overlap. A0, the set of all matrices A such that the weight of A is less than or equal to m divided by log m. Aj, for j going from 1 to D, the set of all matrices A such that the weight of A is greater than m divided by log m, but less than and equal to m. And there are at least m divided by log m to the power of 1 divided by d non-zero elements in this set Ij. Ij is the set of indexes Ij where there are some entries some entry ai1 until id, where we use ij, which is not equal to 0. We notice that the weight of a has to be less than m divided by log m, so it will belong to a0, or it has to belong to one of the sets a1 to ad. There must exist an index j, at least one index j, such that the size of ij is greater than m divided by log m to the power of 1 divided by d. If no such index j exists, that means all the size of ij is less than if we multiply m divided by log m to the power of 1 divided by d times, which is m divided by log m. And that's not correct because we assume that they have more than m divided by log m to the power of 1 divided by d. So we prove that a is all the a0, a1 to ad. Using the probabilistic method, we give d plus 1 sets of d tuples of vectors s1 to sd for each set. S0 to sd we give a set of d tuples such that for every j in 0 and d and a that belongs to aj, there exists a d tuple of vectors x1 to xd in sj such that the entry ax1 to xd is not 0 and all the sizes of the sets equals to the O that we defined here. Case 1. A is in A0. As in the proof of lemma 2, it can be shown that for randomly chosen vectors xi1, xid that are in 0, 1 to the power of n and a in A0, we have the probability that the entry equals to 0 is less than or equal to 2 to the power of d minus 1 divided by 2 to the power of d. Each monomial equals 1 if all its participating variables are 1. Since each variable is 1 independently with probability half, the probability giving monomial evaluates to 1 is 1 divided by 2 to the power of d. Randomly uniformly choose k1, we define here, d tuples of 0, 1 vectors xi, where c is a constant. The probability that for all xi we have axi equal to 0 is bounded by 2 to the power of d minus 1 divided by 2 to the power of d, which we saw earlier, to the power of k1 because we want this to happen for all k1 tuples. Therefore, by union bound, the probability that there exists a matrix A of weight smaller than m divided by log m such that axi is equal to 0 for all I is the size of A0 multiplied by the probability. A0 has at most m divided by log m entries. So this is an upper bound we choose from n to the power of d, and we have for each entry p possibilities to choose from. This is less than 1 for some constant c that we choose because this is exponentially in k1. Case 2. A belongs to M1. We start by proving the following two lemmas. Lemma 15. Let U be the set of all non-zero d-1 dimensional matrices with weight smaller than m2d divided by d plus 1. Then, there is a constant c0 such that for any constant c that is greater than c0 and k2 that is defined here, there exists a multiset of d-1 tuple of 0, 1 vectors y such that for every a that belongs to U, the size of the multiset ya is at least k2 divided by 2 to the power of d, where ya is all the indexes I for which a in the yi entry is not equal to 0. Here we have a reminder for lemma 5. That's because we're going to use it in the next slide. Proof. As above, for randomly chosen vector y and any a that belongs to U, we have the probability that a y is equal to 0 equals 2 to the power of d minus 1 divided by 2 to d minus 1. Therefore, if we randomly uniformly choose the vectors of y, then the expected size of yu is greater than k2 divided by 2 to the power of d minus 1 for any a that belongs to U. because this is the probability that is not 0, and we have it for K2 vectors. Using lemma 5, we have the probability that the size of YA is less than K2 divided by 2 to the power of D. We have some algebraic math here. We have this inequality right here because of lemma 5. Therefore, the probability that there exists A in U such that the size of YA is less than K2 divided by 2 to the power of D is the size of U divided by the probability. We said U has at most m to the power of D divided by D plus 1 entries, so we go over all the sum. We choose I entries, and we multiply by the possibilities that this is non-zero, which is p minus 1 to the power of I. This is less than 1 for some constant C0 and all C that is greater than C0, which implies the result, because we said if the probability is less than 1, then there exists as we claimed. Now let U be the set of D-1 dimensional matrices defined in lemma 15. Let A belong in A1. Since the weight of A is less than or equal to m, there are at most m to the power of 1 divided by D plus 1 D-1 dimensional matrices with weight greater than m to the power of D divided by D plus 1. If this was wrong, then we can multiply this number here with this number here, and we'll get that the weight of A is greater than m, which is not correct. Therefore, there are at least Q indices J such that A belongs to U, and Q is m divided by log m to the power of 1 divided by D minus m to the power of 1 divided by D plus 1. Let U tag contain Q indices J such that A belongs to U. Let AU be the matrix where I1 belongs to U tag, and Y be the set we proved its existence in lemma 15. We note that if we go over all the sum of the weight of AU, we get that it's greater than Q K2 divided by 2 to the power of D. From lemma 15, for each AJ that belongs to U, the number of Yi in Y for which AJ is not 0 is at least K2 divided by 2 to the power of D. So, for each of the Q such J, we get at least K2 divided by 2 to the power of D non-zero evaluations. I have a reminder for lemma 13 because we're going to use it in the next slide. Since the weight of AU is less than Q for all I in K2, and by lemma 13 we have, if we go over the multiply of L of the weight of AU, it's greater than the minimum of QP to the power of QK2 divided by 2 to the power of D minus K2 divided by Q minus 1. This is equal to minimum QP to the power of C1 K2 for some C1 constant, which is equal to the minimum of MP to the power of C2 K2 for another C2 that is constant. If we randomly choose x1 to xk2, then by lemma 3 we have probability that for all I in K2, AXIYI is not 0, less than or equal to the multiplier of 1 divided by L of the weight of A, YI to the power of beta. Here we have some algebraic math that we saw similar to what we saw earlier for C3 that is a constant. Therefore, the probability that there exists a matrix A in A1 such that for all xiyi we have AXIYI is equal to 0 modulo P is, we go the size of A1 divided by the possibility. A1 we can choose up to m entries. Each one has p minus 1 possibilities, which is a upper bound which has an upper bound p. For constant C. Thus, the result follows. By symmetry of the coordinates, the argument for A1 holds equally for AJ for all J in D. Now we get our main result. Corollary 5. There exists a matrix M, size Kn, where K is defined here, and every row of M is a tensor product of D vectors x1 to xd, which are in 0, 1, and 2, 1 divided by D, and every M columns of M are linearly independent over Zp. Summary. Our goal was to construct explicit matrices over Zp such that every M columns are linearly independent. These matrices serve as parity check matrices for codes with minimum distance greater than or equals to m plus 1. The goal was also to minimize the number of rows, T, in such a matrix, ideally making it as small as possible while keeping the desired independence. The main result that we got: existence of sparse binary matrices with M-wise independent over Zp with number of rows T, defined here we went over in the paper. Application to classic problems. The constructed matrices solve the coin winning problem, the signature coding problem, reconstructing graph from additive queries problem. Here we have the references that were also mentioned in the paper. Thank you.